In this last section of Chapter 17, we're going to be doing calculations with Gibbs free energy. Three different types of calculations. One would be if we know delta H and delta S. The second type will be if we have a reaction and we can look at the energy of formation. And the third way is we'll look at the temperature cutoff for spontaneous reactions. To begin, let's sum up the relationship between delta H and delta S. We know that delta G, when it is less than 0, the reaction is spontaneous. We know if delta G is greater than 0, it is not spontaneous. It is made up of two components, delta H, which is the heat of the reaction, and delta S, which has to do with the order of the reaction. And so we have either endothermic or exothermic reactions. Remember, for endo, delta H is positive, and for exothermic reactions, delta H is negative. For the order, for something becoming less ordered, delta S is positive, and more ordered, delta S is negative. We also have to consider each of these four different possible states. Looking at the top line here, if delta H is negative and delta S is positive, then we know that delta G is negative. That's exothermic, becoming less ordered, and it is spontaneous at all temperatures, low temperature and high temperature. The second set of circumstances, we have an exothermic reaction, but it's becoming more ordered. So delta G is temperature dependent. At low temperatures, it's going to be spontaneous, okay, because it's going to help those molecules be more ordered. There's less movement. And at high temperatures, it is not spontaneous. I'll just abbreviate that NS. All right, the third circumstance, we have positive delta H and positive delta S. This is endothermic, but becoming less ordered. So it is also temperature dependent. And it's the opposite of the negative and negative situation above it. It is not spontaneous at low temperatures, but is spontaneous at high temperatures. And then lastly, our fourth set of conditions. If delta H is positive and delta S is negative, then we know that delta G is positive and non-spontaneous at all temperatures. In this chapter, we talk about the three different laws of thermodynamics. Just to review, the first law is conservation of energy. We know that overall energy for the universe is going to be equal to 0, and that the systems and surroundings are going to be opposite of each other. So conservation of energy. The second law tells us that delta S is greater than 0 or positive for all spontaneous processes in the universe. Whoops. For all spontaneous processes in the universe. The third law tells us that the entropy of a perfect solid crystal at absolute 0 that's 0 Kelvin, is 0. So we're not going to achieve absolute zero in normal laboratory conditions. So that tells us that most of the time entropy, particularly change in entropy, will be a positive quantity. We know the further that we get away from this solid crystal at low temperatures, if we go solid to liquid to gas in this direction, entropy will increase with each phase change and the complexity of the molecule. This chart shows the relationship between solids, liquids, and gases and their corresponding entropy values. If you look at our simple solids, iron, which is a single element, has an entropy of 27.3 joules per mole Kelvin. And then as we get bigger in mass and complexity, entropy will increase. Then when we compare this to liquids, liquids have higher entropy because, as a rule, the molecules are more disordered as we go from a solid to liquid to gas. Okay, so going this direction. And then lastly, looking at the gases, chlorine gas has an entropy of 223.1. So again, we see that as we increase in size and go from solid to liquid to gas, that entropy increases. Gibbs free energy is summative, just like enthalpy and entropy. And the name of this law, if you remember from the first semester, is Hess's law. So we can take two half reactions and sum them together. And then we can also take their Gibbs free energy values and sum those together. If we reverse a reaction, let's say I have A going to B and delta G is negative 31 kilojoules. If we reverse that reaction, B going to A, delta G, the only thing that we do is we change the sign. It becomes positive 31 kilojoules. And if I go in and I multiply by some number, 2A going to 2B, just multiplied by 2, then delta G is negative 62 kilojoules. I just take that Gibbs free energy value and multiply it times whatever integer I multiplied the whole reaction times. And that is called Hess's law. For the rest of this video, we're going to look at some examples, calculating delta G in different ways and applying it. Let's take a reaction, nitrogen gas plus 3 hydrogen gas goes to 2 NH3 gas, and we want to know what delta G is and whether or not the reaction is spontaneous. We can look up these values for delta H and delta S in Appendix 2 in the back of your textbook, or you can simply look up the energies of formation on your smart device. But it is in your textbook and it is in the chapter as well. So our delta H values for nitrogen and any pure element or a pure substance in its elemental state, which will have a free energy of formation of 0. NH3 is negative 45.9, and delta H is in kilojoules per mole. Delta S, nitrogen is 191.6, hydrogen is 130.7, and ammonia is 192.8. It's very important here to note, though, that this is joules per Kelvin because we have to multiply through by temperature. And for these, unless we state otherwise, we assume room temperature 298 Kelvin. Okay, so we're going to use the sum of the products times moles minus the sum of the reactants times moles to find out what delta H and delta S are, and then we can calculate delta G. Delta H is equal to 2 times a negative 45.9 minus 0 plus 0. And this gives me negative 91.8 kilojoules. So this tells me that it is exothermic, this reaction. Delta S is equal to 2 times 192.8 minus the sum of 191.6 plus 3 times 130.7. Then I get 385.6 minus 583.7. When I add those together, I get negative 198.1 joules per Kelvin, or negative 0.1981 kilojoules per Kelvin. And I like to put it into kilojoules. It makes the next part much easier. Right, now we're going to plug into our Gibbs-Helmholtz formula. Delta G is equal to delta H minus T delta S. And so I'm going to plug in my three values here. The negative 91.8, negative 0.1981, and 298 Kelvin. Right, so delta H is negative 91.8 kilojoules minus 298 Kelvin times negative 0.1981 kilojoules per Kelvin. So those terms will cancel out, and I get negative 91.8 kilojoules, and that's a minus of a minus here. So that's plus 59.03 kilojoules, which gives me overall negative 32.8 kilojoules for my delta G value. So as I understand this, at this particular temperature, it is spontaneous. Right, in this problem, it's similar to the way we worked the last one. So we'll go ahead and write this. NH4Cl, which is solid, goes to, that's ammonium chloride, goes to HCl gas plus NH3 gas. And same thing, we're going to calculate delta H, delta S, and delta G, and then answer the question about whether or not it's spontaneous. So delta H values, negative 314.4, negative 92.3, and negative 45.9 kilojoules per mole. Delta S is 94.6, 186.9, 192.8, and this is joules per Kelvin mole. Now I don't write moles there because that's one of the things we do is we multiply by moles for each value. In this case, it's 1 all the way across the board. We don't have numerals to indicate any more than that. All right, so let me start with delta H. Delta H is equal to negative 45.9 minus 92.3. We're adding those together. Minus a negative 314.4. And that gives me negative 138.2 plus 314.4. And that's 176.2 kilojoules. And it's positive, so it is endothermic. Delta S is equal to 192.8 plus 186.9 minus 94.6. So that's 379.7 minus 94.6 equals 285.1 joules per Kelvin, or 0.2851 kilojoules per Kelvin. So for the entropy, we know that it is becoming more disordered. All right, now let's plug those in, those numbers, and get our delta G value. Delta G is equal to 176.2 kilojoules minus 298 Kelvin times 0.2851 kilojoules per Kelvin, 176.2 kilojoules minus 84.96 kilojoules, and our delta G is 91.2 kilojoules. It is not spontaneous at this temperature. Looking at the values, they're both positive, so it will be spontaneous at higher temperatures. So it requires high T. In this example, we're going to solve for temperature. We want to know the temperature at which delta G becomes spontaneous. And we're given three different temperatures: 298 Kelvin, 715 Kelvin, and 855 Kelvin. So we're going to solve for delta H and delta S, and then solve delta G. The reaction is 2 nitrogen monoxide gas plus O2 gas goes to 2 nitrogen dioxide gas. Delta H in kilojoules, 91.3, 0, 33.2. Delta S, 210.8, 205.2, 240.1. All right, so let's calculate delta H first. Delta H is equal to 2 times 33.2 minus 2 times 91.3 plus 0. That's 66.4 minus 182.6 equals negative 116.2 kilojoules. It is exothermic. Delta S, 2 times 240.1 minus 205.2 plus 2 times 210.8. That's 480.2 minus 626.8 equals negative 146.6 joules per Kelvin, or negative 0.1466 kilojoules per Kelvin. Both of these values, enthalpy and entropy, are negative. They're both negative, so this tells me they will be spontaneous at low temperatures. But what those temperature cutoffs are, we don't know yet. So we're going to take a look at the next slide and work this out. In the last slide, we determined that we had a delta H value of negative 116.2 kilojoules and delta S equal to negative 0.1466 kilojoule per Kelvin. All right, we want to solve for T. We know that delta G is equal to delta H minus T delta S. At equilibrium, delta G is equal to 0. Okay, so then we can rearrange the reaction. 0 is equal to delta H minus T delta S, we're going to add T delta S to both sides. So then we get T delta S is equal to delta H. Divide both sides by T. Divide both sides by. Okay, so we have T delta S is equal to delta H. We're going to divide both sides by delta S. So we get a new formula, rearrangement. T is equal to delta H divided by delta S. And this will tell us T where it changes from either spontaneous to not spontaneous or the other way around. In this case, because both are negative values, that temperatures below this cutoff point. So below this T will be spontaneous, and above this T will be not spontaneous. All right, so let's plug and chug now in this formula. T is equal to delta H, negative 116.2 kilojoules, divided by negative 0.1466 kilojoules per Kelvin. When I do that math, I get 792 Kelvin. All right, so what that means is this reaction is spontaneous below 792 Kelvin and not spontaneous above that temperature. So we were told 3 different temperatures when we first set up the problem: 298 Kelvin and 715 Kelvin will be spontaneous. 855 Kelvin will be not spontaneous. This last problem is a Hess's law problem. We have a reaction, Fe2O3, solid iron 3 oxide, plus 3 carbon monoxide, goes to 2 iron solid, plus 3 CO2 gas. And I'm given 2 half reactions that we're going to sum. We have 2 iron plus 3 halves oxygen going to iron 3 oxide. I know delta G for that half reaction is equal to negative 742.2 kilojoules. The other half reaction we have is carbon monoxide plus 1/2 oxygen goes to carbon dioxide. And delta G for this half reaction is negative 257.2 kilojoules. All right, so I need to make these 2 reactions sum to equal this one on top here. So we'll draw a line. So I'm going to have to either reverse it or multiply it in order to get it to cancel out to equal that reaction. All right, so if I look at the first one, I know that iron 3 oxide is a product and iron is a reactant, and that's opposite to what I have up here. So I need to reverse that top reaction. It becomes iron 3 oxide goes to 2 iron plus 3 halves oxygen. And I reverse the reaction, so delta G, all we do is reverse the sign, becomes positive 742.2 kilojoules. Now the next reaction, I've got 1 carbon monoxide and 1 CO2. Up here I have 3 of each. So I want to multiply the whole reaction times 3. 3 carbon monoxide plus 3 halves oxygen goes to 3 carbon dioxide. And for that I need to multiply delta G times 3. Delta G is equal to 3 times negative 257.2 kilojoules, which gives me negative 771.6 kilojoules. Now I can cross out terms that are the same on both sides, which is our 3/2 oxygen, and everything else is either only on reactant or only on the product side. All right, so I'm going to sum all of that together. I get iron 3 oxide plus 3 carbon monoxide goes to 2 iron plus 3 carbon dioxide. And I just sum the two delta G values together, which tells me it's negative 29.4 kilojoules. So it is spontaneous, and we were able to manipulate the half reactions to give us the top reaction above. All right, so we looked at 3 different ways to solve for delta G and work problems. The first type was from delta H and delta S free energy of formation. The second type was the temperature tipping point, is another way to say that. And the third example was a Hess's Law problem. We will do a Hess Law problem in class when we meet, and then we'll work some problems similar to this on your own.